So last we arrive at the cerebral cortex, the outer bark of the brain, which again I think is what many people think of when they think of the brain. Um, it is one of the most derived structures, evolutionarily speaking, particularly in humans, who show some of the biggest differences in our forebrain or cerebral cortex structure compared to other mammals. You can see that with both the size as well as the increased volume by doing the folds, right? That is we need more volume, we need more neurons in there, but we can't just grow our heads bigger and bigger and bigger, right? So to squeeze more volume in there, we get all that folding that we see. You'll notice, for example, like in the manatee, it's completely smooth. There's substantially less neurons in the forebrain here of the manatee, whereas in the chimpanzee, we see some partial folding. And we see that also in things like the raccoon and the zebra. We'll see it in rats, dogs, and cats. But in primates, and humans in particular, we see substantial amount of volume squeezed into the skull. There's a lot of brain tissue here. It's 300 billion connections. It is organized into two hemispheres, the left and the right, as we already talked about, and then each hemisphere is divided into four lobes: the frontal, the parietal, the temporal, the occipital, and each hemisphere has all four of those lobes. So there's a left frontal, a right frontal, a left temporal, a right temporal, a left parietal, a right parietal, a left occipital, a right occipital. Early on, researchers who were trying to explore the function of the brain, one of the first places they did is they took a look at the tissue under a microscope. And what they found was that there was some commonality between certain regions of the brain, but also substantial differences. What we're looking at is cerebral tissue and sliced into columns. And you'll notice there are these rows, right, that are called lamina rows, and then you have these columnar, which are also different. So there are some distinct rows as well as distinct columns. What they did is this was done predominantly by a guy named Brodmann, who then divided the brain up into regions based on the similarity of the rows and columns of the tissue in the brain. And he hypothesized that those regions that had similar looking structures under the microscope had similar functions, and he called these areas Brodmann areas. It turns out now with fMRI and additional research, Brodmann was bang on. This approach is called cytoarchitecture and is actually a very effective way of differentiating specific functions in the brain. For example, Brodmann's area is what allows us to produce words, produce sentences. If damage to Brodmann area occurs, you cannot produce sentences, though you can understand them. Wernicke's area, here Brodmann area 22, is what allows us to understand words. People with damage to Wernicke's area can speak fluently, but struggle to understand what people are saying to them. And so the cytoarchitecture is very effective at understanding the function of the brain. So here in the very posterior part of the brain, we have what is called the occipital lobe. The occipital lobe helps us process visual information. Right? This is damage to this area causes what we call cortical blindness. The eyes function normally, but we can't process and make out what we're seeing. This often creates what we call blind spots, which are regions where we can't see color or shapes or maybe see at all. Right? So this contains the primary, secondary visual cortexes and helps us process and break down what we are seeing. Superior to the occipital lobe, and in the most dorsal part of the brain here, we have what is called the parietal lobe. The parietal lobe is where incoming sensory information tends to be processed. When we break down the parietal lobe, what we see is individual areas of the body are clustered into tight clusters of neurons, and those sense what's happening in those particular areas of the body. In fact, we can look at what's called the homunculus, which shows us actually the density of different areas of the body. So this little homunculus looks a little weird, but this is a human sensory homunculus. The larger the body part, the more sensory neurons dedicated to that region. The smaller the body part, the less. And this should make some sense, right? That we can navigate the world much better with our hands than we can our torso or our elbows. Right? Our lips and our tongue are very sensitive. This helps, yes, with tasting and eating, but it's also hugely important in language and language production. Right? Our eyes, our nose, our ears all have a disproportionate amount of sensory neurons dedicated to them for the size of the anatomical structure. Inferior to the parietal lobe and the frontal lobe, and in the most lateral part of the brain, we have the temporal lobe. The temporal lobe contains things such as the auditory cortex, which, like the visual cortex, helps us process raw sensory information, but in this case, auditory. It also is housed to other sensory systems. One very interesting one is what we call proprioception. Proprioception is understanding where your body is in space. If you close your eyes and move your hands around, you know where your arms, your hands, your feet, your legs are in relation to your other body parts and where they are in space. That is proprioception. Disruption of proprioception can cause a series of odd hallucinogenic experiences. For example, in temporal lobe epilepsy, people who experience disruption in the temporal lobe often experience disruption of proprioception and often perceive of themselves as being outside of their body, right? And this is what we call an out-of-body experience. Right? This is when somebody views themselves as being out of their body. Hodoscopic is where you see yourself and another entity, but you're not sure where your consciousness is. And then otoscopic hallucinations are fairly rare, but they do happen, which is where you perceive of yourself as being in your body and see a sensory version of yourself out in the world. This is sometimes called the doppelganger effect, where you might walk into a room and suddenly see yourself sitting at your desk, right? And this is due to, we think, to disruption of proprioception in the temporal lobe. The final region is the frontal lobe, and this is in the most anterior part of the brain, in the very, very front, and is an area of the brain that has shown substantial development in humans. Now, we talked about the cerebral cortex shows dramatic development in humans. It is the frontal lobe where we see the greatest amount of development. And this is an area of executive function, of goal direction. In fact, we can modulate and see how goals are processed in the brain by actually looking at the flow of information from the anterior to the posterior part of the frontal lobe. For example, if your goal is to make a sandwich, what you find is the big picture goal, right, is in the most anterior part of the frontal lobe. Your goal is to make a sandwich. But as we move more to the posterior part of the frontal lobe, you begin to get into the component pieces of how that could be executed, such as spreading the peanut butter on the bread. And in the most anterior part of the frontal lobe, it is the specific motor responses that allow us to do this. Right? The frontal lobe is hugely important in executive function, decision-making, modeling, and in all of the sort of judgment aspects that many of us consider our day-to-day conscious mind.